All right. So my name is Sukhmanu Lal. I'm with the Water Institute at ASU, and it's my pleasure today to have Anthony visit us. Um, so he's at this Yale School of Architecture now, but I met him the first time when I was at Columbia, and uh, once he talked about what he had been doing, my reaction was that I'm in the 19th century, and I should say Dr. Livingston, I presume, because he had walked over a large part of North India and documented those travels in this amazing book, uh, which represented what is going on in the Ganges Basin. And I had never seen anything like it. So my reaction was, wow, I didn't think people in the 20th century walked. And especially they didn't walk those kind of distances and collected data and drew maps by hand. It was remarkable, truly remarkable. So he gave a talk at Columbia, which was in the old French school. Um, and what was interesting about it, in a sense, was that before that was the French school, it was the mental hospital. So you had to wonder whether somebody who did what he had done belonged in the mental hospital or in the French school. But he also had a whole bunch of these drawings that were put up on the walls there. So from a conversation point of view and from an expression of what was going on the ground in India, that was truly remarkable. So I think you're in for a treat because this is version 2.0 or 3.0 of that story. And I'm really interested to see the connection to climate change because it is the story of groundwater, in my view, is really much more poignant than climate change because we have taken something that has been in the ground for 1,000 to 100,000 years and changed that, which is clearly more significant than the climate change story, which is of a much shorter duration. So let me welcome Anthony. Uh, I look forward to the talk and hold your questions to the end um, and write them down if you forget, because you're going to find that there are going to be so many points at which you would want to ask something. Okay. Let's welcome Anthony to the podium. Thank you.
Thank you, Manu, for that really kind introduction. As someone who's long admired your work, I really means a lot to me, and it's really wonderful to be here. Although I have to say, we miss you on the East Coast, but Arizona is incredibly lucky to have you. As Professor Lal was mentioning, I've spent quite a bit of time doing research in India, across South Asia increasingly, but especially in India, and I'm going to connect it to your backyard here in Arizona as it relates to questions of groundwater. And the work that I'm going to share with you this afternoon, I wanted to show just the team that's gone into making this possible, a little bit like the film credits at the beginning of a movie, because there's quite a lot of work that goes into this in terms of producing not only the drawings and scholarship, but also the exhibitions. And part of what I do as well is exhibit this work on groundwater and the River Ganga or Ganges. So before I talk about the exhibitions that I have up currently in London, that's on display at the Wellcome Collection, as well as at the Venice Architecture Biennale, which all of this is part of that work. And why I came to organize an exhibition really around these core samples that I'll tell you a little bit more about, and why I hang them over mirrors. I'd like to begin with 3 measurements: 80 centimeters, 979 cubic kilometers, and 99%. 80 centimeters is how much the tilt of the Earth has shifted between 1993 and 2010 because of how much groundwater we've extracted from it. 979 cubic kilometers is how much groundwater was extracted in 2018. That's a little over 2 Lake Eries in terms of the amount of water that's taken out. And 99% is groundwater accounts for 99% of the liquid freshwater stock on Earth and is the world's most accessed freshwater reservoir. And I share this with you because for me, we live in the groundwater age. Groundwater is integral not only to agriculture, but cities and for drinking water. And the work that I'm going to share with you tonight especially focuses on two of the largest places of groundwater extraction, which happens to be India, which consumes more groundwater than the People's Republic of China and the US combined. And then Pakistan comes in a fourth. So South Asia, and particularly Asia, is one of the largest consumers of groundwater in the world. And here I'm breaking it down in terms of industrial uses, domestic consumption, and irrigation. And the fulcrum, as it were, that's allowed for this shift to happen and for so much groundwater to be taken out are these things known as tube wells and hand pumps. And it's millions of these instruments that have shifted the tilt of the earth and allow for so much groundwater to be extracted on a daily basis. And tube wells and hand pumps are commonly used in places where municipal water supply is non-existent, unreliable, or often polluted. These are minor technologies with a global reach. They tap into one of the largest masses of fresh water on the planet, aquifers. And as you can see here, they do so in a variety of ways with different depths, volumes of abstraction and extraction. And tube wells are typically constructed from perforated steel or plastic pipe, even sometimes bamboo, that's bored anywhere between 1.5 meters and 300 to 400 meters below grade. And they're typically driven by either an electric or diesel-powered engine. And once the water is extracted, it might be consumed at the surface by people, like here, outside of New Delhi. You can see a diesel tube being used. You also find instances of tube wells like this on your right, another diesel-powered tube well or a pump powered by diesel, pulling out water from a surface water body, this being a canal, to irrigate agriculture. Or oftentimes one finds them, the electric-powered ones, in buildings like this in Punjab, or even in parks like in Lahore at Shalimar Bagh. And certainly one finds pumps scattered all throughout the landscape in front of houses. You can find cast iron pumps outfitted like this one, unironically with a plastic water bottle attached to it. And certainly in urban environments as well, like this instance of one in Kanpur. So you can see the ways in which it brings animal husbandry together, urbanization. It's used for drinking water, for both water buffalo and people, also for washing clothes. And it might even be distributed like in water tanks, as you see here, which is increasingly being done across the subcontinent and in many other parts of the world as well. And today, nearly half the global population drinks groundwater on a daily basis, and over half of all agriculture is irrigated with it. These devices, as I'll share with you, have allowed billions of people to thrive, but today they threaten to bleed portions of the earth dry. And my contention is the following, that groundwater extraction technologies are as significant to farms and cities as the elevator was to Manhattan in the first half of the 20th century. And while this has largely been reported as a catastrophe in the making by the media, and I'm just going to share a few screenshots from the New York Times about everything from, say, the East Coast sinking to America using up its groundwater like there's no tomorrow. This one kind of surprised me, groundwater being used for chicken wings and pizzas. Certainly kind of the uncharted waters and those with power thwarting conservation efforts, to policies put in place, like here in Arizona, to attempt to balance urban growth and the availability of water in the face of scarcity and uncertainty, to looking at how, say, Meta's data centers require so much water to keep them cool that they are rapidly depleting aquifers, to looking at where groundwater levels are falling and rising globally, all of which is critical and important. But I would say most of this is not focused on how this plays itself out spatially. So this afternoon, I'm going to largely speak about understanding hand pumps and tube wells, along with their owners and users, as reshaping space, both agriculture and cities. And I've weighed in on this in my own way a few years back when I penned an op-ed on the need to consider space and time as factors for replenishing aquifers, for urban growth and agricultural production, with, again, a focus on shaping space. And my work certainly builds on a body of scholarship that ranges from, say, B.D. Doven's work in the 1970s to Dubash's work on tubewell capitalism and the formation of institutions around this, mostly in the context of Gujarat and Western India, to rural economists like Tushar Shah, who looks at the ways in which tube wells redefine social systems, mostly in South Asia, to Arid Empire by Natalie Koch, who I believe will be speaking tomorrow here at the university, and the ways in which we have technological transfer between, say, the state of Arizona and Saudi Arabia. And I've been, in effect, writing for some time now and published bits of it, a biography of the tube well. It came out of a sense of people write poems to rivers, even to canals, but nobody writes poetry for tube wells. It's quite an underappreciated instrument, and yet it's so critical to the way that we live today. And have been developing this again even further in terms of its impact, especially in South Asia and also here in the Sonoran Desert. And now making use of groundwater, I want to be clear, is not new. Our species has been doing this for at least over 3,000 years. Say we can look at a qanat, or it's also called a falaj, which is effectively a way of tapping into an aquifer and bringing that aquifer to irrigate agriculture, like you see here in the section up above for date palms in the Middle East. And we can find these infrastructures all across the Middle East through Western China and in South Asia and Eurasia as well. To say the Persian wheel, which most likely came to the subcontinent over 700 years ago, but was developed in 200 BCE as a way of drawing up groundwater using a bullock to pull up water with the Persian wheel that you see here to irrigate crops. And certainly we find even still to this day Persian wheels and mots like you see here to, again, draw up groundwater. And we have public infrastructure or civic architecture or hydraulic architecture like stepwells, bowlies that you see here that both collect monsoon waters and connect that to the aquifers. But oftentimes these have been left to kind of be overtaken by trees and weeds, as you see here, because they've been replaced by and large by tube wells. And the portability of the tube well, coupled with industrialization in the 19th and 20th centuries, along with the murky codification of groundwater rights here in the Americas and Asia, made them well suited for military campaigns and for areas with little or no surface water bodies. And because of my interest in understanding this condition spatially and over time, I've been drawing the different kinds of configurations of pump technologies across the globe and placing them in relationship to agriculture and urban growth. So these are just kind of 9 instances of different spatial relationships to tube well technologies. Oops. And so these drawings examine tube wells and hand pumps as lenses for observing this largely yet critical infrastructure that I would define as groundwater earth, which is that portion of the Earth's invisible hydrological cycle that undergirds global agricultural production and urbanization. And what do I mean by that? Well, in 2002, the Gravity Recovery and Climate Experiment, known as GRACE, was launched. It's composed of 2 satellites orbiting the Earth, and it's really the first opportunity to directly measure groundwater changes by space. And by observing changes in the Earth's gravity field, scientists could estimate changes in the amount of water stored in a region with cause changes in gravity, or which causes change in gravity. And so monitoring these changes allowed scientists to visualize and calculate the size and volume of water in aquifers. But to give you some sense of the level of resolution, most satellite imagery we get is like 30 meters to the pixel. This is 230 kilometers to the pixel. So it's incredibly low res in terms of what it provides, but it gives us a sense globally, and it's still very much used for climate modeling. But what I'd like to do is imagine if we don't so much picture the globe in terms of its different gravitational poles or conditions, but instead, what if we were to empty the globe of its surface water bodies, a little bit like what Thomas Burnet did in the 17th century, and instead of doing it to try to show the veracity of Noah's flood, instead to better understand the relationship with topography and bathymetry. If we do that with this globe, I can then take the satellite imagery that's provided by GRACE, and I can start to map out the relationship between aquifers in terms of volume and density to the topography and bathymetry of the globe, so that I can better understand this relationship between the surface and subsurface of the planet. And this modeling took about 2 years to do just because of the double curvature. But I take sections through then 2 of the major sites of extracting groundwater, here in the Sonoran Desert and in the Indo-Gangetic Plains that you can see here on the right-hand side. And then I take this section and I effectively take that circle and I unfurl it in a straight line, which you can see here, using SkiLab as the data to better understand again bathymetry and topography to aquifers. So understanding that kind of thickened condition of how we extract so much from below, and here then take that portion of the globe and unfurl it and make it flat at the bottom of the drawing. And I do all of that so that I can do models like this that's currently in Venice of the Earth, aquifers, and here are kind of America, North America's aquifers in relationship to the bathymetry and topography of the globe. So again, inside and outside. And I focus on these 2 places that have contributed mightily to those 3 measurements that I mentioned to you before of 80 centimeters, 979 cubic kilometers, and 99%, which is again the Indo-Gangetic Plains and the Sonoran Desert. And this work is the outcome of nearly 2 decades of fieldwork and archival research, where I've moved like a sinusoidal wave between fieldwork and archival work to build these models. And if, as the historian Swati Chattopadhyay argues, urban forms have a direct correlation with infrastructural norms, then in the absence of nature and the state, cities and towns, as well as farms and homes in the Indo-Gangetic Plains and the Sonoran Desert, share similar patterns of water extraction. As 2 of the world's most intensively pumped landscapes, these regions can tell us a great deal about how people use tube wells to tap into the larger global commons of groundwater resources that are not only unevenly distributed, but also unevenly accessed. And before I do that, let me fill in a little bit of the backstory to tell you why I've spent the better part of these past 2 decades trying to see like a mud skipper, which is pictured here. These beautiful amphibious fish can live on land for days on end. And what's more, they move between wet and dry, hard and soft conditions. Indeed, they're mud-loving creatures that have inspired a lot of my work that I'll share with you today. And they not only move between these areas with ease, but they have evolved so that when they are above water, they see clearly like we do. Whereas when we submerge ourselves, our vision becomes wavy due to how water refracts light differently than air. But mud skippers continue to see clearly below or underwater as well as above. And this kind of double vision can teach us a lot about how to not only reckon environmental uncertainty, but also incorporate it in our work as stewards of the built environment. And hopefully they can assist in seeing beyond barren dichotomies like hard and soft, wet and dry, land and water, groundwater and surface water. So as Professor Lal had mentioned, I spent a decade seeing like a mud skipper to create a dynamic atlas of the Ganges River Basin. And I'm not going to try to shoehorn that work in tonight, but suffice it to say that the principal argument is that imagine I take the footprint of the river, the watershed, and I tilt it at 45 degrees. I then look at all of the rain-fed agriculture and all of the irrigated agriculture, like you see here. It is like a vast hydrological supersurface. There's no other part of the planet that has that continuous kind of irrigation like you see there. And so it's a hydrological machine. But this hydrological machine is less like a device, like say a chronometer that's pictured here that was used to establish longitude. And instead, it's more like Luke Skywalker's bionic arm in The Empire Strikes Back. Is it a technology with a biology, or is it a biology with a technology? So I'll share with you some mud-loving moments that epitomize the virtues of sitting like a mud skipper, which means attending to this substance here, silt. Ever since the subcontinent collided with Asia 50 million years ago, trillions upon trillions of tons of silt have been shed from the ever-growing Himalayas. So these tectonic crumbs, as it were, are part of the process of understanding this basin and why it's become such a space for agricultural production and groundwater extraction. Now, this is a drawing of what I would say is one of the main architects of the subcontinent, which is the monsoons, which is a fire-water cocktail produced because of the difference of the subcontinent mass to the Arabian Sea and larger Bay of Bengal and Indian Ocean. And I've been spending quite a bit of time over the past 2 decades in this city that's known as Allahabad, or today Prayagraj, where the Ganga, or Ganges, that you see to the north meets the Jamuna River, or in Delhi they call it the Yamuna. And then there's said to be a third river that meets here, the Saraswati, which is where those 2 rivers come to meet that you see there. And it's located at a major site for Hindu pilgrimage, as well as a major artery in terms of historic transportation. And I know it's a little hard to see here, but the waters to your right are blue and the waters to the left are brown-gray. And while this looks like it's 2 water bodies coming together, it's not. It's 2 geological provinces coming together, because the Ganga River is fed by sediment from the Himalayas, whereas the Jamuna River, the blue, is fed by the Chambal, which has a very different sediment load. So this is what makes these 2 rivers have these 2 different colors that one finds oftentimes in the ways that they're pictured. But it's, again, the bringing together of these very different tectonic crumbs within this site, and which has shaped this landscape for so many millennia. And the drawings of the confluence and its environs that I'm sharing with you here combine cartography and photography to capture the cyclical rhythms of the monsoons over the course of a single year. So what do I mean by this is this drawing shows how surface water bodies like riverbeds, lakes, and ponds expand and contract over the course of a single year due to the monsoons. Observing these slow motion changes are crucial to understanding the urban form and urban life of the city and its environs. The lighter tones of violet are when the surface water bodies swell with the monsoons, and the darkest tones are at their shallowest and thinnest. So throughout 2005 and 6, when I first moved to India, I visited the confluence every 2 weeks, where I snapped photos like you see here to create a panorama, to be able to better understand how this area goes from arid and dry to wet and gelatinous silt every year. And these panoramas show or complement the slow motion changes that I shared with you of those tones of violet. So where I'm documenting those things cartographically from above, here I'm doing it photographically. And so this set of panoramas is during the month of Magh, from Magh Mela, which is a festival where 2 to 3 million people move into a temporary tent city. We have water, like plumbing, we have electricity, toilets, there's temporary hospitals. And this space is inhabited for 45 days. But when this is over, the festival ends, the outline of the grid remains tattooed on the sandbars and shoals, farmers move in to sow crops and harvest them. And so in other words, the banks and sandbars are transformed from this hyper-dense urban to agrarian space in less than 2 weeks' time. The farmers harvest their crops. The monsoons arrive, eroding the sandbars and shores, and completely washes away the ground. This process of urban to agrarian repeats every year. And it's definitely the most intelligent use of space that I've ever seen in terms of how people incorporate the deep rhythms of the monsoons. And here, these are then all of those panoramas and drawings put together, and they've made their way into documents like for the UN as a way that you might start to draw the biophysical, but also sacred geography, social, political layers of a city. And this is also the site where the Kumbh Mela, the most recent one, happened this year. These photos are from 2013, where every 12 to 13 years, a temporary city is built here for 45 days. In 2013, it's believed 80 to 100 million people came here. This year, the government of India said that between 400 and 500 million people came. I'm not sure about those numbers. I didn't feel that many people when I was there, but it is quite impressive that you have these temporary structures that are covered in canvas, but made of bamboo, pontoon bridges. This tent city that exists with hospitals. It's inhabited 24 hours a day. But what's more incredible to me is that it goes from this to this in 2 weeks' time. That's that same bridge that you see there. And it goes to agrarian space, and all of that silt and sediment that's collected here over 50 million years acts like a giant sponge, with one able to strike groundwater in less than 20 centimeters to irrigate your crops, like you see here. And you can see here the footprints of those tents and avenues remain tattooed on the sandbars. It's literally a drawing at the scale of the territory. So these drawing processes, I would argue, provide a blueprint for how to build on these deep rhythms of the monsoon, a process that I think more and more parts of the world would benefit from with climate change and greater environmental uncertainty. Now, I began this work in 2004, and I think it's important to contextualize this. Some of the best books I could find were, say, Raghuveer Singh's The Ganges, which is a photo essay. There were madcap adventures like Slowly Down the Ganges, where Eric Newby and his wife go from Haridwar, where the Ganges enters into the Gangetic Plains, to the Bay of Bengal. And by the end of it, his wife divorces him because of what a arduous trek it was to travel with him, to say histories of cartography, avalanches of numbers, like you see here. Google Earth had just gone live. Drones existed, but were mostly being used by the Bush administration to surveil or assassinate people. Gray satellite existed, as I mentioned to you before, but really low resolution. So all I had was a really clunky Garmin eTrex GPS and an even clunkier Nikon camera to try to map out this watershed. And when I got to India, I had hoped that I would find contemporary maps. And I would ask, and these were oftentimes the best that I could find from the Survey of India, which were usually tracings of maps from the 1950s and 1960s. So effectively, it hadn't been carefully mapped or surveyed comprehensively in over half a century. And when I would ask if I could see maps, people would oftentimes say, well, why are you CIA? And I don't know anybody who would say they work for CIA. I certainly haven't. But so I had really no other choice if I wanted to carry out this work but to walk the land. And I'm showing you these photos, not because of how bad I look with long hair in this dust storm that's happening because of all the silt, but because I became my own barefoot hydrographer, cartographer, and historian to do this work. And here you see a dust storm brewing because of all of that silt and sediment that's been shed here. So understanding the river basin as something that is as much water, but also mud, dirt, dust, deity, atmosphere, and so much more. So I went from Gangotri Glacier, which is about 3,800 meters above sea level, through the Gangetic Plains, taking about 25,000 photographs, a near continuous panorama of it. And seeing like a mud skipper also led me to making my own instruments, which were prosthetics that I would wear. So because it hadn't been mapped in half a century, I developed guerrilla tactics to measure these changes through devices like this surface accumulation sleeve, which is a prosthetic that one wears on their right arm to map soils. It's equipped with that clunky Garmin GPS system that you saw, as well as rolls of packaging tape, so that just to say when Spider-Man shoots his web from his wrist, I shoot packaging tape from my arm to collect soils. And I do that perpendicular to the river edge, like you see here, to collect these soils for a kilometer. And here you can see the way that I exhibit this instrument in Seoul. These are using Walking Dead figurines because they were the right scale to do these kinds of dioramas. Or here a close-up of that instrument that I made in order to do this. Using this thing, 45°C weather is quite arduous, so I developed different versions of it that were a little bit more comfortable. And also then using a kind of radio antenna as a hoe to pat down the tape. And then even reconfiguring a child's remote control car into a surface accumulation rover, tricking it out like you see here with packaging tape, torch, camera, and a lot more to do this work of collecting soils to map out this area, which also doesn't hurt one's back as much. Then along with these rolls of tape, which get very big and collect so many things, I also developed what I call a Gunga dip sock, where I bought 100 pairs of white cotton tube socks and would thrust them into the river all along its banks from Gangotri Glacier up in the Himalayas to the Bay of Bengal as a way to collect soils. I would then geotag them and dry them off, like you see here. So that when I went through customs, and if I got asked, well, why do you have all these soiled socks? I would just say that I was a filthy backpacker that didn't have time to do my laundry, as a way of bringing these soils in and managed to get them past government officials to do this work. But if I bring you back to this tape as a way of looking at the soils, the tape that, along with it being like Spider-Man's web, it's a lot like Katamari Damacy, if any of you know this Nintendo game from 2004, where small objects like spoons and paper clips adhere to this little orb for this prince that's trying to build a new galaxy or a new set of planets. And so eventually jungle gyms start to stick to this, and even entire cities collect, and city blocks and stadiums. Well, my strands of tape, they collect soils, but also flowers, fecal matter, plastics, auto parts, and many other things. So these artifacts from human and non-human occupation allow me to conduct an ethnography of the soil. Using the wrong thing for the right purpose defines most of my work with water, soil, and urban form. And seeing like a mud skipper then means using these devices to be able to move between the space of the laboratory and the space of the field. And after scanning many hundreds of kilometers of packaging tape, I didn't have any instruments to analyze the soils. So I turned to that trusted Photoshop tool, the Magic Wand. Now you might use the Magic Wand to say if you want to digitally impose a tattoo on someone's chest. But I misused the Magic Wand tool to break down particle sizes. And here again, using the wrong thing for the right purpose allows me to make my own remote sensing device when no data is available. So here I'm breaking down the different sediment sizes because those particle sizes tell you about the behavior of the riverbed and flood channels that I look at. And that's what then allows me to make much larger drawings of the watershed, not just of the city of Allahabad, but these transects, like you see here, where again, I'm able to plot out those tones of violet and dark violet and light violet by using these instruments. So I always like to think of these drawings in fashion terms. If most cartographic drawings are customized, say like something you get by Christian Dior, they're like couture. Mine are more like ready to wear that you get at Uniqlo or Target because they have a seam allowance. So you can gain a few pounds, lose a few pounds, they still fit. So these drawings are not outdated by the time they're done because they take into account surface water and groundwater conditions in relationship to urban form and urban growth. And they allow me to not only then look at, say, the surface, but also subsurface. So I start to take those and understand the relationship better between the surface water in the river channel with the groundwater and aquifer, like you see here, mapping out then the different layers of water extraction by tube well, urban form, cultivation or fields, all the way to the cropping patterns that one has in different fields. So it's quite transscalar in what I can do with it. And it's built up or built upon then all of this silt that makes this area such a productive area for agriculture, with the highest level of groundwater potential in India being within the Indo-Gangetic plains that you see at the top. And throughout this process, I would often find advertisements like this, where we see a yeoman farmer speaking about the virtues of this Crompton Greaves tube well of drawing up more groundwater. And it's always drawn in section. It's always drawn in relationship to the aquifer and what you can do with it. And there's a reorienting that's happened across this area from thinking of the surface to the subsurface. And what I mean by that is that this is a drawing that goes from river all the way to tube well on the right-hand side. And you can see that we go from very dense to much less dense with the tube well, because the tube well allows people to effectively domesticate areas for agricultural production, but also urbanization, and not have to stick so closely to surface water conditions, whether those are rivers, canals, etc. So it allows for a diffuse kind of urbanization to take shape. And I look at the history of the tube well in a much longer time wall that I won't go into depth about. But I think what's important to note is that this was initially developed in 1865 in the United States as a military technology, patented because there was a concern by Union soldiers that Confederate troops in the American South would poison surface water bodies. So this was a military technology for drawing up groundwater. It's eventually adopted in the UK and by this gentleman by the last name of Norton, that uses it for agricultural production and brings it to all of these agricultural shows in the UK. And eventually it's used in the Abyssinian desert in modern Ethiopia to draw up groundwater for a British expedition in the 1860s. And I share these moments with you because it's traveled from the US to the UK to Africa. It eventually makes its way to the subcontinent, where it's used and then is oftentimes spoken about as the Abyssinian tube well because of its health benefits. It's not exposed to any atmospheric influences, is the way that they would describe it in the 19th century. And it gets profiled in the Lancet, Scientific American, as this scientific engineering technology. Now, it's important, though, in the context here in Arizona, because, as many of you probably know, in 1898, there was a court case that came before the Arizona Territorial Supreme Court regarding the ownership rights to an allegedly well-defined subterranean stream that ran beneath a person's property a little bit to the north of Sedona. And the claim was that someone purchased land from someone who had been using tube wells. Their neighbors were using tube wells as well, and even drilling more tube wells. And effectively, the person that purchased the land sued their neighbors because they said that according to first in time, first in right, like here in Arizona, you can't compromise someone's access to surface water bodies for drawing water. You can draw up water, but you can't impact theirs, or let's say reduce theirs. He claimed that his neighbors were reducing it. So it goes all the way to the US Supreme Court. And in short, the argument was that the subterranean water was the same as a surface water body. But in fact, when it goes to the Supreme Court, they uphold the decision of the Arizona Territorial Supreme Court, because what they see and what they describe is this. They say that groundwater is not recognizable like a surface water body because it percolates and oozes from the ground. It is therefore a constituent part of private and not. it's both an architect and historian of science, because that has a lot to do with how do we draw and define groundwater. So this is a film from the 1935, during the Great Depression, to describe the relationship between surface water and groundwater. Yeah, groundwater as being a part of property. This is changing in other parts of the world, and certainly you obviously have your AMAs here that I'll talk about in a moment. But while Arizona is developing its system of groundwater extraction, we have the longest canal system in the world, the Ganges Canal in the Indo-Gangetic Plains. It's about 12,000 kilometers long today, with a very large central water bureaucracy. This canal system was developed in the middle of the 19th century, continues to grow even to this day. But in the 1930s, the falls, the artificial falls of the canal system, are outfitted with turbines to power electric-driven tube wells. And it was to power about 88 villages, about 600,000 acres with 1,500 tube wells. And these buildings still exist, mostly as sites where people scrawl their lovers' names or donkeys hang out, like you see there. But it was an attempt to try to bring together energy, agricultural production, to monitor and oversee agricultural production in the Indo-Gangetic Plains. Eventually, these tube wells go more and more diesel powered, but they're also very integral to the Green Revolution, where high yield variety strains of wheat and rice are used in the subcontinent, as well as to the south of here in the Sonoran Desert. And I share you this image because we see here a Punjabi farmer with high yield variety wheat over his right shoulder. Then we see a tube well here irrigating the farm. We see DDT being sprayed, and then we have a tractor in the background. So these crops require more water, pesticides, machinery, but also credit to finance this. And they also have new institutions to develop, like Punjab Agricultural University. So there are new institutions being formed, new practices that are happening around and needing to rely on groundwater extraction. And of course, you can make the jump between this and this. It's always still very much pictured as a condition that's applicable to the farmer. And what's unique too, though, I would say, is in a place like India, we've more recently had green tribunals to try to oversee and regulate groundwater extraction. But here in Arizona, you have a much longer history of this with your AMAs or active management areas. And I'm obviously not going to be that person that comes and tells you about your place and the kind of Groundwater Management Act of 1980. But I think suffice it to say, this civil code that develops recognizes that groundwater should be understood as something as shared as the air we breathe. So all of the tube wells and bore wells here obviously are metered in these active management areas. And while I know that this was a larger state initiative to try to manage groundwater, of course, it's dropping precipitously, especially those hundreds of thousands of year old, or say, I think mostly here, I want to say it's 40,000-year-old water, right? The groundwater that you have here. Well, the work then that I do is to try to not just see and plan, but also to better understand these conditions in section. So I try to see a little bit like a geologist does in terms of the stratigraphy, like you see here. I do that as well, but I do something a little bit different. Produce, but it obviously drops water table levels. You see that it then so it's intention, and I put mirrors underneath it, like you see here. so that we understand that this is a major protagonist in shaping how we terraform this. So when you come to the mirrors, so these things that look like Pringles here, those are those strata that you see here. When we come to the mirrors, we can see reflected in them the surface to better understand the ways in which we terraform by extracting so much from the subsurface. So you effectively look down to look up, and you look up to look down in the exhibition. And I do that at 4 scales. I do that at the house scale, the neighborhood, the city, and the hinterland scales. And I do this always looking at a core sample here in the Sonoran Desert and in the Indo-Gangetic Plains. So for instance, if I take the scale of the house, I want to share with you 2 houses, one that was built in flowing wells here in Arizona, not terribly far, just next to Tucson, and another house that was built in New Delhi around the same time. And both these houses incorporate tube wells and wastewater management as an essential domestic infrastructure. And by bringing these 2 technologies into the domestic sphere, the home no longer relies on any centralized water management system, and allows for a greater flexibility in terms of location. So let me begin in New Delhi. This is the first Prime Minister of India, Prime Minister Nehru, and then this is Jacqueline Cherwit, a South African planner who is brought in by the United Nations to design a model village. And there are over 100 model houses that are built here for this village. You know, houses like this, where you have kind of a barrel vault, or even this one that was made by the asbestos industry in India at the time. But none of these houses recognize where water will come from. They all assume it will be through a municipal system, except one, which is the growing house that was designed by a chemist that worked for Monsanto for many years and then is employed by the Indian government. And he designs a house where there is a hand pump in the center, kitchens flank the house, and then we have here multi-generational family housing that develops always around this courtyard with access to the hand pump. And so you can see in this section here how it's at the center of the house. And here it's also taken into account keeping the animal husbandry, the mangers, and the bathrooms as far away from the hand pump as possible, so you don't have wastewater infiltrating into groundwater. But effectively, it allows the builder of this house to create their own oasis. Now, this same kind of pattern exists here in the Sonoran Desert. So this house that was built in flowing wells around the same time in 1957 has a tube well and is outfitted with a septic tank so that it too might function as an oasis. But of course here, the tube well goes much deeper. And here you can see the septic tank within the neighborhood of flowing wells where it's located. So very similar patterns of spatial aggregation around the extraction of groundwater. And so I then hang those 2 models of the houses in relationship to one another to understand better groundwater here in New Delhi versus groundwater here in the Sonoran Desert. And I do this also at the scale of the neighborhood. So of course you have Winter Haven here in Tucson, which was designed to look like Shaker Heights in Cleveland, Ohio. Has anybody ever been to Winter Haven before? There's a very big Christmas tree, Christmas light extravaganza that happens here. But to me, what's more amazing is that they created a neighborhood municipal water supply, a cooperative, so that they could irrigate their lawns to always be green year round. So this is the edge of Winter Haven and non-Winter Haven here, where you can see the desert floor butts up against the grass. There's obviously an aesthetic project here, but there's also a sense that this is a community shared resource. I'm not advocating for doing this kind of lawn keeping, but at the same time that this was being developed here in Arizona, Loney, which was a town of 4,000 people in 1961, is today over 500,000 people. And it survives by originally supposed to have a similar tube well system like Winter Haven, but instead has over 14,000 hand pumps, mostly in public places along streets and open areas, to supply groundwater for drinking for these 500,000 inhabitants. But when you have so much buildup of impermeable surfaces, the groundwater level is dropping. And so we have hand pumps going dry in these areas at the neighborhood scale. And so I've developed two projects that I'll speak briefly about that address these issues in both these locales to think better about how do we conceive of groundwater as a collective civic infrastructure. So in the context of Loni, where we have that buildup of impermeable surfaces, you can literally see that they're overtaking even the hand pumps here in terms of all of the brick and building that's being introduced. And it's quite a densely populated neighborhood. This is then a satellite image drawn in figure ground, where white are the buildings, black is the open space. I introduce a micro infrastructure that's here, 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 into this area in this figure ground, which is effectively introducing a covered roof that you see here, because there's an incredible amount of heat island effect here, introducing then across 3 city blocks, new schools, clinics, and shops that are very much needed, and then this open space here. But beneath these blocks are a very large system then of cisterns that are designed to collect rainwater. So instead of everybody having their own hand pump or bore well, all of the rainwater is collected from the roofs of the neighbors in the block, and we then will artificially recreate the groundwater cycle of using sand in these cisterns to collect that water to better keep it for public use in each of these blocks, and also so that it doesn't get wastewater infiltration along with all of the heavy metals and microplastics that are now in this soil here. So here, taking architecture and making it using architecture to transform groundwater into a public good and a public space under a single roof, and doing this in different areas of the neighborhood. In the context here then of Tucson, I look at the Foothills Mall, which is oftentimes spoken about as a dead mall because it's been abandoned and now torn down, many parts of it. And I look at this mall because it has an incredible amount of surface parking area that you see here, and of course also experiences inundations and droughts. And how might we then transform these large spaces of capitalist consumption at a mall into a larger collective infrastructure? So here what I've designed is effectively a very large park that would collect all of the runoff and rainwater with housing along its edges and recreation here. The housing tiptoes over this much larger area for artificial groundwater recharge, so that then transforming this area of large-scale parking and consumption into a larger common good that could be replicated in other places. So I share these with you not as finalized designs, but as provocations of what could be done, of how design could bring an understanding, again, of how we better incorporate the subsurface to shape the surface of the planet. And City then showcases at that scale overdraft in New Delhi and here in Phoenix, Tucson mega region. And in both cases, depleted aquifers are causing major subsidence of the earth due to the compacting of soil, which you all probably know. What we get develop like these that I know you all are so familiar with, that happen because of the extraction of groundwater. And this is very much like a tornado or a hurricane. It does not care what's public and private land, yet it raises all kinds of questions because of mostly atomized private extraction of groundwater about who's responsible for repairs to buildings, who insures these spaces. So it raises larger collective questions because of our thirst for groundwater and how it plays itself out. In the context of a place like New Delhi, this is next to the on the airport because the runways are also sinking as a consequence of both the planes and the consumption of groundwater. So we also have sinkholes that develop too. At the larger regional scale, the hinterlands bring together how underground water can be understood in the battle between greenfield urban development and agricultural uses. In the case of Phoenix and Tucson here, new urban development has consistently replaced agricultural land. And in the case of New Delhi's periphery, new large-scale urban projects coexist in a dramatic juxtaposition with agricultural uses. So of course, you all know this quite well with the pivot irrigation, the 1785 land ordinance, or the Jeffersonian grid, as it's called, in terms of how that plays itself out of these kinds of development butting up against pivot irrigation, like you see here. And in the context of, say, New Delhi, we find in a place like Noida, just outside of it, tall towers cropping up alongside agricultural plots due to the value of real estate, all of which relies on private tube wells. So in an attempt to make sense of these conditions, I make portraits of cities. So this is a portrait. See the city? City. Here you can see it a little bit better. You can see that this is a much larger collective infrastructure than that ring road, than that metro, yet we don't think about this as a public infrastructure, supporting so many millions of people through these millions of tube wells. And here you can see that a little bit closer. And of course, the depth of them on this side is different than this side because of the Delhi Ridge and the kinds of soils we have here versus over here. And here again, then better kind of foregrounding those conditions. And I compare then everything from New Delhi to Phoenix, Tucson, we're at right now in terms of the tube wells. And what's amazing about Arizona is that in all of your AMAs, we have the depth and volume of every single one of these bore wells. So these are all true to depth in the Phoenix, Tucson mega region. And again, your metro system much smaller than New Delhi's, but we can see here this vast commons. And I can keep doing this. I do this with Mexico City, like you see here. I do this with Addis Ababa in Ethiopia and Jakarta, which is the fastest sinking city in the world. This is the Bay of Jakarta. And these are all of those tube wells that allow for that city to thrive, but also are introducing saltwater infiltration into the groundwater because of over-extraction and being next to the coast. And in my exhibition, then, I place those portraits in relationship to these patented technologies to better understand how these technologies have been used to shape both agriculture and cities. And in these portraits, we can see the ways in which the tube well in aggregate is greater in its scale than those metro systems that I mentioned. In much the same way that the case before the Supreme Court here in Arizona drew attention to how we draw and define groundwater. Similarly, how might we think and draw groundwater differently as a collective resource that undergirds the shaping of cities in the 21st century? It's imperative to understand aquifers as a commons in much the same way we share the air we breathe. And it's crucial to tie urban form and groundwater together to be able to envision urban spaces where the private pump is no longer king. Now, if you're the only person who can think in a specific way, you might be brilliant, but you're going to lead a very lonely revolution. So sharing work across diverse mediums is of the utmost importance. And I try to do this in the work that I do through books, exhibitions, op-eds, and teach to engage larger audiences on the topic of groundwater as one of our largest shared commons. As more and more of the world faces environmental uncertainty, exploring groundwater should goad us to use our skills to both interpret the world and project the world. If we are unable to give a civic dimension to the presence of this vital resource, then we're likely to suffer the consequences of sight without the benefits of insight. Thank you.